Hi there! This video series is to display my problem-solving and learning abilities. I hope to show that I can solve any programming problem, regardless of whether I already have expertise in the language at hand. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. For now, I am learning Python. I have no professional experience or formal training in the language, and have only been learning it since mid-January. While I'm picking up fairly quickly, I cannot claim any real expertise. Today, I am going to show my approach to solving the 9th Project Euler problem, starting fresh and talking through my thought process. As always, I will link to both Project Euler and my repository in the description. Let's dive in. So, problem 9, special Pythagorean triplet. Pythagorean triplet is a set of three natural numbers for which a squared plus b squared equals c squared. Yep. There exists exactly one Pythagorean triplet for which a plus b plus c equals 1000. Find the product ABC. Okay, so numbers that add up to 1000. And we are looking for the product. Okay, let's try to copy this whole thing. It's of course not going to copy everything because the Project Euler website puts images for some of this. But let's see. Gotta create our problem 9.py. I'm not sure of a great way to put this, so I'm just going to say a squared plus b squared. Equals c squared. So, and this was a plus b plus c equals 1000. Okay, is that the correct problem? Well, I have A, B, and C in the incorrect order here, apparently. Minor things. But it's always the minor things that bite you, so you gotta pay attention to them. Okay, so we're basically looking for a number. Okay, so I think that we should have a function where we find out is Pythagorean. And this will take, let's just have it take ABC. That's not the symbol I meant to type. And here's this terminal again, opening up when we don't want it to. So if So, for anyone who does not know, this is actually valid Python syntax. It looks a little bit strange, but it does function the way you would expect. And let's see, so... times A plus B times B equals C times C. There might be a more elegant way to do this. Oh, right. And instead of having an if and then return true, we can just do return. Okay. So we have our little function. Let's go ahead and print. Let's test it out with one of our examples, just to be safe. So 3, 4, 5, which is the one I think we all learned in school. That's not what I meant to do. But I mean, it's good everything's up to date, right? Okay, so true. Excellent. Now let's do one we know is not Pythagorean, so 3, 4, 6. That was false. We could obviously do a lot more tests for a little baby function here, but I don't think it's necessary. I think just the 2 will show that it works well enough. Okay, so we basically need to cycle through, I'm gonna say 1, 2, 9, 9, 7, because 1 plus 2 plus 997 equals 1000. Oops, caps lock is on. So for I in range 1998, because it will not include the end of the range there. And then for j in range, I actually really like this little range function. It's very convenient. And then for k in range 3. 1000. So, as you can obviously tell, this is not super efficient. We're doing what is essentially an algorithm with an O of n cubed. The only reason we're going to be able to get away with this with any kind of speed is this is only 1000. And 1000 cubed is still like nothing for a computer. At least in the Python language. So let's see. We want to test if A plus B plus C equals 1000. Oops. I named them IJK over here, didn't I? And is Pythagorean. IJK. Then we want to print A times B times C. Or, again, what did I name my variables? And actually, at this point, we just want to be like, we're done. So, what is it? Exit? I think there's a better command here. Let's just try exit, see what it does. Okay, so for I in range, and honestly, like, I don't love this. I want to start at 999. Oops. And go down to 2, which is only going to go to 3. Have it step negatively. That'll make it just a tiny bit faster, I think. But this might be pretty slow. Let's go ahead and copy our timing strings that we have. I honestly quite enjoy being able to do this little part because it's just really nice to have an exact count of how long your program took to run. Okay, so if we run it now, we should get some number. And it's taking more than a second to run, which isn't a wonderful sign. But let's give it a little bit. So apparently I was wrong about 1000 cubed being nothing to the computer, but... And it looks like this exit does not work the way we want it to. Let's go ahead and go look at how to exit a Python program, which I have definitely looked up more than once before. Python exit. Oh, well, if you call it like a function, it might work like a function. Cool. Let's go ahead and stop that. Run it again real quick. Looks like it takes 22 seconds to run the, at least through to what I am hoping is the correct answer. According to our prompt, there is exactly one Pythagorean triplet, so this answer should be the correct one, and it looks like actually calling this as a function instead of just having the word exit here did work for us. And this time it took 23 seconds, so pretty consistently and definitely within the 1 minute limit that Project Euler gives us. But is it the correct answer? Yes, excellent. So that's pretty cool. Let's add, since that only took us about 12 minutes, let's go ahead and see if there's a nice little document in this one, because sometimes I like to see whether I picked the most efficient algorithm. And it looks like they start with the straightforward approach, which is, of course, what we did here. Actually, before I dig into this, is there a more efficient way that I could have done this? I could not do the range of k. Let's go ahead and implement without this third range. So k is just going to be equal to 1000 minus I minus j. And then we need to take all of these lines and move them over a little. So that obviously is going to improve our functionality quite a lot. And then we actually don't even need this check because it will always equal 1000. So let's see how much faster this is. So previously our primary running time was like 23 seconds. Now it is less than 1. And we got the same answer. Is there another way of doing this that would be more efficient? Let's look at the document, because that's That's the best I can do really, really quickly on my own right at the moment. Let's see. Using a parameterization of Pythagorean triplets. Okay, this is getting a little deeper in math than I actually know, I think. Yeah, this is getting very deep into the weeds of math. That is a little more than, I can particularly understand right at this exact second. I'm sure that if I studied it a little bit, I could get it. It looks like this one... Yeah, these all look a little more complex. Yeah, it gets into figuring out the slopes of what I presume are right triangles. And yeah, lots of maths in this one. Let's look at this actual code algorithm and see. Let's see, so in limit is the square root of s2 minus 1, so fair enough. Or maybe the integer version. Not sure what this does other than make an array. So we start with an m at 2, and then if s2 mod m, so if it's evenly divisible, then sm equals s2 divided by m. And then reduce the search space by removing all factors of 2. Yeah. Once again, this is a little bit deeper in math than I usually go. Okay, then 2m. Interesting. So, yeah. I don't know if anyone in my audience can understand this super well based on just looking at it for as long as I'm looking at it. But I'm certainly not in the best of headspaces to figure it out quickly on camera. But I think the fact that my straightforward approach, which this says sufficiently fast enough for small enough s but doesn't scale well, yeah, that is correct, yes. If you multiply the value of s by a factor k, the span of each of the two loops is multiplied by the same factor, since the loops are nested, etc. So, if s is doubled, the program takes approximately 4 times as long. Increases. So let's little... Yeah, so this algorithm is definitely unsuitable for parameters s greater than 1,000,000. Which is valid. But also, this was the question, and we did solve the question, and we were able to improve the algorithm to the point where it ran in, like, 1 second. Less than a second. I'm not displaying milliseconds, and maybe I should. Let's, just for curiosity's sake. I think this is how you do milliseconds. I might have to look it up if it doesn't work. It's how you do milliseconds in other languages. Yeah, that's not it. Let's see. Python. Date time. Milliseconds. looks like it's like this. You know what? Instead of going to Stack Overflow, let's see if we can find some actual... Doesn't look like we're stumbling upon any great solutions right away, but let's just do the F. Well, we have to change both of them if we want both of them to show up, don't we? And I do think that this gets a little bit faster as you run it over and over again, so this won't be a perfect test. But yeah, you can see here that it ran in like a very, very small amount of time. And as the article rightly points out, this won't work if you keep making the numbers arbitrarily larger. So I don't actually even know if there is one for 10,000, but let's throw that at our little algorithm real quick and see just how much slower it is. Okay, so it actually did find one, and perhaps not surprisingly, it's the exact same number with some more zeros, but it did take 6 seconds to run, which is many, many times longer. So you can just kind of see just from that, like, the importance of efficiency once you get into numbers that are of any size at all. And since I am not currently a math expert, that's, I think, the best we're going to do for today. And perhaps someday I'll come back and look at this and be like, yeah, yes, exactly. But today is not that day. And it is definitely better to know these non-straightforward approaches that are so much more efficient. Part of my goal with looking at Project Euler problems is to increase my efficiency. So hopefully I can get that a little bit better throughout this series. And yeah, that is about it for today. I'll see you in the next one.